I think it's all set. Now it's all Ryan's control. And, thank you.
Okay, thanks, Juven.
Let me try to hide the bar, the zoom bar. How to do that?
What do you want to hide?
The zoom bar, I think it is like hide video panel. I think it is hide video panel. I hope that this is the correct thing.
You can make it smaller. I don't know about hiding it. I don't see it on your screen.
Oh, you don't see it? Okay.
No, so it's
but
not
I
in the
see
way.
it. All right. Maybe I put it at the top, hopefully.
So let's just wait a couple minutes for people to filter in. Okay, shall we get started?
Yeah, all right.
Okay, so welcome to the CMSA Quantum Matter Seminar. Today, we're happy to have Mohamed Anber from Lewis and Clark College. He's here to tell us about generalized Hooft anomalies in vector-like theories. So please, go ahead.
First of all, thanks a lot for the invitation. Today, I will be talking about the generalized Hooft anomalies in vector-like theories. Hooft anomalies is a topic that gained a lot of momentum during the last few years, and it is in the interest of a large group of people in high energy physics, in condensed matter physics, and in mathematics as well. But today I will be talking about Hooft anomalies from the point of view of high energy physics, given my background. This talk is based on this work, as well as these three works with Eric Poppets. So why we are interested in Hooft anomalies? In fact, Hooft anomalies provide a unique handle to study non-perturbative phenomena in strongly coupled quantum field theory. And let me mention that there are only very few handles on the non-perturbative phenomena in QFT. This includes the large N limit, the ADS-CFT, which also demands taking the large N limit. And if you want to go beyond the large N, then this is always challenging. And we also have the lattice field theory. However, you always have to be careful interpreting the data that comes from the lattice simulations. In this regard, Hooft anomalies is an exact technique that doesn't require taking the large N limit, nor putting the theory on a lattice. So in this regard, it is unique. So Hooft anomalies put severe constraints on the infrared spectrum of asymptotically-free gauge theories. And in the past and currently still, they are being used to put constraints and study composite quarks and leptons, and also study dualities. This includes the cyber dualities. And recently, there has been used to classify the symmetry-protected topological phases of matter. Hooft anomalies were known since the 80s. However, the anomalies that were introduced by Hooft today are known as the zero-form anomalies because they are associated with zero-form symmetries that act on local fields. In this talk, I'm going to use the word that either zero-form anomalies or traditional Hooft anomalies or the conventional Hooft anomalies. However, during the last few years, due to the work of these gentlemen, we understood that there are also what today we call the generalized global symmetries. And the generalized global symmetries can also become anomalous. So these generalized Hooft anomalies can be used to put further constraints on the spectrum of a strongly coupled theory. So I told you that why we are interested in Hooft anomalies, but I haven't told you what is an Hooft anomaly. So given a global symmetry G of a quantum field theory, we may try to gauge G. And here I am being very specific because by gauging here, I mean turning on a background gauge of G or background source of G. So I don't sum over gauge bundles of G, and this is important. So if the symmetry is obstructed, then we say that it is anomalous. And we say that the theory has an Hooft anomaly. So in this regard, the Hooft anomaly is not something bad within the theory. There is nothing. There is no sickness within the theory. It is a way to study the theory. And the 't-Hooft anomaly, as any other anomaly, is a renormalization group invariant. And hence, it is extremely useful to study asymptotically-free gauge theories. Because in the UV, you can compute the anomaly coefficient C using perturbation theory, for example. And then you flow to the IR, and the coefficient C has to be exactly reproduced by the IR dynamics. However, the theory becomes strongly coupled in the IR, and you cannot solve it. And you can come up with scenarios. However, whatever scenario you come up with, it has to exactly reproduce this coefficient C. Now, the matching of, this is called the 't-Hooft anomaly matching procedure or conditions. And the matching can be motivated by either using the spectators or the Stora-Zumino descent equations. So in this talk, I'm going to raise a few questions and answer them. So these questions are, given a quantum field theory with a global symmetry G, what is the most general obstruction to gauging G? In this regard, I would like to discuss the generalized 't-Hooft anomalies. And the second question is how to match the anomalies in the IR. And the third question is, can anomalies teach us about new or old IR phenomena? So these are the three questions I'm going to answer in this talk. So let me start with the big picture. So I will consider a symmetry G, and this symmetry G in general could be internal or space-time symmetry. However, for the purpose of our talk today, I will concentrate only on internal symmetries. In general, I can write this G as G1 cross G2. Sorry, this should be subscript 2 cross etc. Okay. And I can mod by some discrete subgroup H, and this modding by discrete subgroup H is going to be extremely important for the purpose of the generalized 't-Hooft anomalies. Then I'm going to play a game, and here is the rules of the game. First, I will start with a well-defined four-dimensional asymptotically-free gauge theory with fermions in a general representation and symmetry G. Then I will turn on a flux F sub G of the symmetry G that is compatible with the theory. And I will try to make this flux as general as possible and compatible. And this is a key word here, because I cannot just turn any flux. It has to be compatible with my theory. Then I will examine the partition function Z in this background flux as I perform a global transformation with G or one of its subgroups, G1 or G2, etc. If the partition function picks a phase or a C number, then we say that this is the 't-Hooft anomaly. I can do this computation in the UV. Then I can flow to the IR, and here I will assume that my theory gets strongly coupled. And of course, I cannot solve it. However, I can propose a spectrum that matches the anomaly of the UV. So this phase has to be exactly matched in the between the UV and the IR. Now, how the matching happens? The matching actually can happen due to Goldstones or domain walls. So basically, you can break your global symmetry. If the symmetry is continuous, you have Goldstones. If it is a discrete, you have domain walls. You can match the anomaly by forming composite massless fermions in the IR. You could also have a topological quantum field theory or a conformal field theory. Notice that in all situations, whenever you have an 't-Hooft anomaly, this excludes a trivially gapped phase. And by this, I mean a single vacuum that is gapped. This is what I mean, trivially gapped phase or trivially gapped vacuum. So in this talk, as I mentioned, I'm interested in turning on the most general fluxes in vector-like theories, and hence I am trying to see the most general anomaly that I can have both on spin and non-spin manifolds. So what is the ultimate goal of doing that? The ultimate goal is to eliminate as many IR proposals as possible. And I represent this using these Venn diagrams. Let us imagine that these three circles represent three different Hooft anomalies. And you see that they intersect in a smaller area, which means that they actually constrain my theory in the IR more than only one Hooft anomaly can do for me. So the more anomalies you have, the better, because in this case, I can eliminate as many scenarios as possible, and I can pinpoint to a narrower variety of scenarios. So my talk is basically divided into three parts. In the first part, I will study anomalies on spin manifolds. In the second part, I will study the anomalies on non-spin manifolds. And finally, in part 3, time permitting, I will discuss one application, which is the deconfinement of quarks on axion domain walls. There is actually a question here. Is each a subgroup of the product space constructed by GIs? I will be very clear about what I mean by H in my talk. So you will see that in a specific example, what I mean by that. Okay, so anomalies on spin manifolds. And I will start with the textbook example, which is the QCD with three fundamentals. So this theory has the following global symmetry. It is U1 baryon cross SU3 left cross SU3 right. And basically, it has the following anomalies. It has SU3 left cube anomaly, and U1 baryon SU3 left square anomaly as well. Or you could also replace the left by right. And you get these anomaly coefficients, NC and NC. One important thing to notice about this anomaly that it is a traditional or a conventional Hooft anomaly or a zero-form Hooft anomaly. And you can see that because this anomaly is associated with turning on an integer topological charge of SU3. All right. And the matching is via the here happens via the Goldstone bosons. So basically what happens is that the SU3 left cross SU3 right breaks to SU3 vector. And one can prove that the composite massless fermions cannot match the anomaly in the IR. And one can show that using group theory as well as number theory arguments. And then it was shown by Witten back in the 80s that a Wisdomino-Witten model of the Goldstones can match this anomaly in the IR. But the question is, are there more fluxes we can turn on in this theory? And are there more anomalies? So these are the kind of questions I am trying to answer in this talk.
Excuse me.
Yes.
So just make sure, should the center of SU3 left and the center of SU3 R, which each of them are Z3, these two Z3 are identified and should be also shared by the U1.
That is correct. That is correct. Yes, yes, that is exactly correct. Actually, yeah, I'm going to mention that. Yeah.
Okay.
All right. So in my attempt to consider these generalized Hooft anomalies on spin manifold, I will start with one example that has been thoroughly studied during the past few years, which is the Qcdr joint. So basically, we consider SU and C gauge theory with the NF flavors of adjoint Weyl fermions. By the way, all the Weyl fermions I am going to talk about in today are left-handed Weyl fermions. Now I would like to show that the faithful color group of this theory is not SUNC, but rather it is SUNC mod ZNC. And this is because that the fermions are in the joint representation, and hence they cannot see the center of the group. So in order to show that, I will need a bit of differential geometry. However, I will just make a disclaimer first. I am very far from being precise, so I don't really want to be very mathematically precise. I just want to convey the idea. So my apologies to the mathematicians and mathematically oriented people. So a bit of differential geometry. Let us consider a four-dimensional manifold M, and this manifold admit a spin structure. So we can put the fermions on this manifold. And the manifold can be covered by batches. And let us consider the overlap between two batches. Let us call them UI and UJ. So you can define the fermions either on the batch UI or on the batch UJ. And then you want to make a coordinate transformation between UI and UJ. So you say that your fermion in batch I is associated to the fermion in batch J using what we call the transition functions, Gij. And these transition functions are valued in the adjoint representation of SUNC. Now, in order to make sure that your theory is consistent, you have to demand that on the triplet overlap between three batches, UI, UJ, UK, the following cocycle condition is obeyed. This is basically a consistency condition that is telling you that your theory is well defined globally on the four-dimensional manifold. This is always important to satisfy. But let us now think about how you can build the Gij in the joint representation, how you can build the transition function in the joint representation. We just need to recall that the adjoint representation in Young tableau looks like it takes the following form here on the right, and we have to realize that every single box in the Young tableau basically is an element of the defining representation of our gauge group. So schematically, I can write Jij in the joint representation as the multiplication of Gij in the defining representation NC times, because I have NC boxes. Of course, in general, you have to take care of the symmetrization and the anti-symmetrization. However, this is not going to be important for our purpose. Why? Because I will be interested only in the element of the center of our group, the nth root of unity. So now you see, okay, because I'm interested only in the center element, when I multiply Gij in the defining representation NC times, I get unity. So Gij in the joint representation basically goes like 1, and this is why the fermions don't see the center of the group, and this is why we say that the faithful group that acts on the fermion is SUNC mod ZNC rather than SUNC. Now, this is my cocycle condition written in terms of the Gij in the joint representation, and I can rewrite it like that if I use the Gij in the defining representation. This is actually telling me that it is consistent to turn on a flux of my center without spoiling the structure of my theory. So this is what I'm going to do next. I can turn on a fractional flux. This is a ZN center flux on my manifold. If you think that previous treatment was a bit abstract, let me implement that practically. So what actually I'm going to do is the following. I am taking my manifold to be a 4 torus T4, which is a spin manifold. And I'm going to turn on the center fluxes, also known as Hooft twists, by the way, because they were used by Hooft back in the 80s to study pure Young-Mills theory on a torus. I'm going to turn on these fluxes on 2 of the 6 different planes. Let us say, for example, X1 and X2 and X3 and X4 planes. So for example, in the X1 and X2 plane, I am going to write down my gauge field as follows. First of all, I am taking my 4 torus to be a symmetric torus with a cycle length L. And you see here that A1 takes the form of a large gauge transformation. H here are the Cartan generators. There are NC-1 Cartan generators, and the nu are the weights of the defining representation. I can do the exact same thing in the X3, X4 plane, and then I can do a simple computation to find that the charge, the topological charge associated with this flux I am turning on is fractional. As you can see, it is 1 minus 1 over NC. In fact, there and using this construction I will just tell you about in a moment. Sorry, actually, I mean, do you hear me? Because I feel that there is some interruption with the internet.
Yeah, it's fine.
Oh, okay. All right. Thank you. All right. So let us consider the following pair of 1 form and 2 form fields, B1 and B2. And they satisfy the following constraint. dB1 is NCB2. Basically, what I am saying here is that B2 is a flat gauge field, as you can see easily by taking the derivative of both sides. Now, the integral of dB1 over 2 cycles is 2 pi times an integer. And because of this constraint here, I find that the integral of B2 over 2 cycles is a fraction. And one can also compute the B2 with B2 on my manifold, on the 4-dimensional manifold, to find that it is also 1 over NC squared. So this is the first step in this construction, is introducing this pair of 1 form and 2 form fields. The second step is to enlarge SUNC to UNC. And then we embed the 1 form BC1 in UNC. So we do this as follows. Let us consider A tilde, which is a gauge field that is valued in UNC. And we write it as the AC, which is valued in SUNC, plus a U1 factor. And I am going to embed the B1 form in the U1 factor. And of course, then we can go ahead and compute the field strength in the UNC group as usual. But the problem here is that I enlarged the gauge group, and hence I introduced 1 extra degree of freedom. And I need to kill this extra degree of freedom. I want to go back to only the degrees of freedom of the SUNC gauge group. In order to do that, I postulate the invariance under the following 1 form U1 gauge field lambda C1. So I say that the A tilde goes like A tilde plus lambda C1, and this is my U1 1 form gauge field. And I also say that BC1 goes like BC1 plus NC lambda C1. Now I can use the field strength F tilde C to find that F tilde goes like that. And I can also use the constraint between the 1 form and the 2 form field to find out that the two-form field transforms as is shown here. Now, it is easily seen that f tilde minus B2 now is invariant under the U1 one-form gauge field lambda C1. This means that if I want to keep this gauge invariance, every single physical quantity I construct in this theory has to have the combination f tilde minus BC2. So using this construction, now I can compute my topological charge, and the topological charge can be now computed by replacing the f with gf by f minus b with gf minus b, and this will produce exactly the 1 minus 1 over nc, the fraction topological charge we found before using the four torus. As a consistency check on our construction, that it is legitimate to turn on this fractional flux, one can compute the Dirac index. And as I will mention in different instances, that the Dirac index basically is a slick way to see that our construction is self-consistent. So the Dirac index in this theory, which is Qcdr joint, is the number of flavors times the Dynkin index in the joint times the topological charge, which is an integer. And basically, this is a reflection of the consistency of our theory, or in other words, the satisfaction of the co-cycle condition. Now, we can recall that the Qcdr joint has a discrete chiral symmetry. It is Z, 2n, C, and F. And I can examine the partition function in the background of the fractional flux as I perform a transformation with the global discrete chiral symmetry. So I find that my partition function makes this phase, and this is exactly the Hooft anomaly of the discrete chiral symmetry in the center background. And this anomaly has to be matched in the IR, and the matching can happen, for example, by forming domain walls. So basically, the discrete chiral symmetry is going to be broken down to Z, 2, and F in this case. So this example explains the idea behind this generalized Hooft anomaly. Now, what I would like to do is to take this construction and to generalize it for any vector-like theory. So I am going to consider SUNC with NF flavors of Weyl fermions in a representation R plus the complex conjugate fermion. Here I am actually going to concentrate only on complex representations. So this is the group assignment. I have psi and psi tilde. Both of them are left-handed Weyl fermions. Psi, as I mentioned, transform in a representation R, while psi tilde in the complex conjugate representation. There are also two flavor groups, SUNF1 and SUNF2, such that psi and psi tilde transform in the defining and anti-defining representation, the fundamental or anti-fundamental. And there is also U1 baryon, such that psi and psi tilde are oppositely charged under the U1 baryon. And the theory also enjoys a discrete chiral symmetry, Z2NF TR, where TR is the Dynkin index in the representation R. And both the fermions have charge 1 under the discrete chiral symmetry. So this is the structure. These are the global symmetries that act on the theory, but not quite. You will see that actually there has to be some modding, and this modding will play a crucial role in finding these generalized Hooft anomalies. So I'm going to play the exact same game I played before in the case of Qcdr joint. Again, I'm going to take two batches, UI, Uj, And excuse me, I'm going to consider a transition function, Gij. And this transition function has to obey the co-cycle condition on the triplet overlap between Ui, Uj, and Uk. But now notice that Gij, the transition function, is made of 3 different transition functions. It is made of Gij of the SUNC gauge group in the representation R, and also of the Gij in the defining representation of SUN flavor, and the transition function of the U1 baryon. So let us consider each one at a time. Let us first start with the transition function of the gauge group in representation R. Now again, you can use the Young tableau of the representation to see how many transition functions in the defining representation you need. You also can take the symmetrization and the anti-symmetrization into account, but this is not important. Actually, it turns out what is important even is not the representation R itself. It is only the nullity of the representation, because as I mentioned before, I'm interested only in the element of the center of the gauge group. So the nullity basically is the number of boxes in the Young tableau mod NC. So basically, I will find that my transition function in the representation R takes the following form. It is the nth root of unity to the power little n, and little n here is the nullity of my representation. So this is for the Gij in the representation R of the gauge group. What about the transition function in the flavor group? Now, because my fermion is in the defining representation, this transition function is going to become an element of the center of the flavor group. But now you see, here I am forming this multiplication between 3 transition functions, and I would like to, or I want to, satisfy the co-cycle condition. Then this is telling me that in order to satisfy the co-cycle condition, the transition function of the U1 baryon has to pick the following phase such that the co-cycle condition is obeyed. As you can see that if you multiply this by this by this, you will get unity. Simply stated. Again, I am being here schematic. I am not mathematically precise, but this is basically the idea. In other words, I can say the following. Let us take 3 elements, U, V, and W, that belong to SUNC, SUNF, and U1 baryon. And then I am doing the following identification. I am identifying U with a center element of the color group, and I am identifying V with a center element of the flavor group, and then I am identifying W with this phase here. So if you think that this is the abstract construction, then I can practically implement it, sorry, excuse me, using my 4 torus. So I can turn on fraction fluxes on the 4 torus using the exact same method I showed before in the case of the Qcdr joint, and I find the following fractional charges. So I have center fractional charge in QC in the color direction. I have also a fractional charge in the flavor direction, and I have the following charge in the U1 baryon direction. Now you see that the nullity of the representation appears in the topological charge of the U1 baryon, basically in order to, and this was necessary again in order to satisfy the co-cycle condition. As I mentioned, it will be useful to go back and forth between the construction of the fluxes on T4 and also using this more formal mathematical language of the pair of the 2 form fields. So here I have to introduce 2 pairs B1 and B2 in the color direction, and B1 and B2 in the flavor direction, such that my topological charges takes the following form in the color, in the flavor, and in U1 baryon. Again, by the same token, I demand that this quantity here is invariant under lambda C1. This is a one-form U1 gauge field that is necessary in order to kill the extra degree of freedom. And I do the exact same trick here in QF. And finally, when I compute Q baryon, I find that this full combination is invariant under both lambda C1 and lambda F1. All right. So now, as a consistency check on our construction, that our construction is a legitimate one, we can compute the Dirac Index. So in order to compute the Dirac Index, we just need some group theory elements here. So TR again is the Dirac Index in representation R, and dim R is the dimension of my representation. And one can show easily that the Dirac Index now is an integer, which is again a slick way of seeing that my fractional fluxes, I can turn on the fractional fluxes on my manifold. Now, let me stop here to comment on one thing, which is the thing I mentioned at the beginning, which is what is the faithful global symmetry that acts on my theory. So one actually can use the identification I told you about before in order to show that the true global symmetry or the faithful global symmetry that acts on the fermions is given by the following modding. Basically, this first factor here, the ZNC over GCD of NC, N, is part of the gauge group, and hence I have to mod it out. ZNF is common between SUNF and U1 baryon, and I have to mod it out as well. Finally, this Z2 here is the -1 to the fermion number, which is a good subgroup of Lorentz, and I also have to mod it out. So basically, this is the faithful global symmetry of my theory. Again, you can see that using this identification I told you about.
Sorry, what is this small n?
Small n is the nullity of the representation. So this is the most general flux. These are the most general fluxes I can turn on in this theory. And now what I actually can do, I can apply a global transformation with a discrete chiral symmetry on my partition function in the background of these fluxes. And I find that my partition function picks up a phase. I'm going to call this phase the BCF anomaly. And this phase can be shown to be belong to or to be an element of the Z sub NFTR or a proper subgroup of it. Of course, depending on the details of the theory. So let me give a very specific example of what does the BCF anomaly buys us, by us, okay? So what extra constraints the BCF anomaly can put on our asymptotically free gauge theory. Let me consider SU4K with NF equal to 1. So basically, I'm considering one flavor or one Dirac flavor in the 2-index symmetric representation. The discrete chiral symmetry of this theory is Z sub 4 plus 8K. First of all, one can show that the theory does not admit fermions. This is because of group theory reasons. The theory has only bosonic states. And then you can, so there is no way you can match the 8 Hooft anomalies in this theory by composite fermions in the IR. Now, what you can do is that you can compute the zero form or traditional 8 Hooft anomaly. And there is the Z sub 48 plus 4 plus 8K U1 baryon square. And this anomaly is valued in Z sub 2K plus 1. Because this anomaly is valued in Z sub 2K plus 1, this means that I can match the anomaly by breaking the discrete chiral symmetry down to only Z sub 4. This means that a plausible scenario that is compatible with the anomaly matching condition is to propose that the 2 fermion condensate is 0, while the 4 fermion condensate does not vanish, leading to 2K plus 1 vacua. So this scenario is consistent with the zero form 8 Hooft anomaly. So now let us see what happens when I turn on the BCF fluxes in this theory. When I turn on the BCF fluxes, I get the BCF anomaly, and now it is valued in Z 4K plus 2, which means that the discrete chiral symmetry has to be broken down all the way to Z2, which is basically the -1 to the fermion number, which is always a good symmetry whenever your theory respects Lorentz invariance. So this means that the previous scenario I told you about is totally excluded, and and this leaves us with the following scenario, that the 2 fermion condensate has to form, and this will lead to 4K plus 2 vacua. So this is an extremely strong statement that the BCF is telling us. Now I can generalize this construction to any SUN theory with fermions in the 2-index symmetric or anti-symmetric representation with a single Dirac flavor. Now, if I assume that the IR vacuum is gapped, so if I assume that composite massless fermions do not form, then the BCF anomaly is telling me that the discrete chiral symmetry, which is Z sub 2n C plus or minus 2, depending on whether the representation is symmetric or anti-symmetric, has to break down all the way to Z2, which means that the 2 fermion condensate has to form, and this leads to NC plus minus 2 vacua. However, I must mention that there is also a caveat, which is the possibility of matching the anomaly using TQFT. This is some interesting possibility that one might want also to think about. Sorry. So now, because this vacua form, then we actually should also include that there has to be domain walls that interpolate between these different vacua. So in this regard, it would be very nice to propose the Wisdom-Witten action that will actually match the anomaly in the IR. Basically, I'm going to write down this Wisdom-Witten action using the trial and error. So let me do the following. First of all, I'm going to write the following action, which basically is a trivial, quote-unquote trivial, topological quantum field theory. The omega 0 here basically performs the discrete chiral symmetry transformation. And A3 is a 3-form field that couples to the world volume of the domain wall. A3 is a U1 3-form field, and the integral of this 3-form field on 3 cycles is 2 pi times an integer. Of course, this is trivial. This will not match the BCF anomaly in the IR, so I have to do something extra. So what I could do is the following. I can just borrow the flux that I used in my UV theory. It doesn't really matter whether we are in the UV or in the IR. It is a flux, so the theory will see it, whether it is in the UV and or in the IR. So I am borrowing this flux that I used to compute the topological charge in the UV. By the way, here I am using NF equal to 1 for simplicity. But yet one can show that this Wisdom-Witten action does not match the anomaly, does not produce the BCF anomaly. So there is something still missing. Okay, so what is this missing piece? It turns out that the missing piece is the B2, which B2 of the center symmetry. Now let us see what is happening here. First of all, let me mention that indeed, one can show that the variation of this Wisdom-Witten action will exactly match the BCF anomaly. But let us see closely what is really happening within this action. First of all, I told you before that this combination has to be invariant under lambda C1. Again, this lambda C1 is a U1 gauge field that was necessary in order to eliminate redundant degree of freedom, or unphysical degree of freedom. And I told you also that every single physical quantity you write down has to be invariant under this lambda C1. However, BC2 is not invariant under lambda C1. It transforms like that under lambda C1, which is telling us that the free-form field that couples to the domain wall has to transform like that under both BC2 and lambda C1. This is telling us that the free-form field is talking to the center to the center flux of the gauge group. By the way, this takes the form of a three-group structure, and is going to play an important role later on in my talk when I talk about the axion domain wall. So this is something extremely interesting about this BCF anomaly, that the BCF fluxes talk to the free-form field that couples to the domain wall deep in the IR. And you can contrast that with what happens in the case of a zero-form anomaly. So in order to see what happens in the zero-form anomaly, all you have to do is just to turn off these center fluxes, just to eliminate the BC2 from the expression here. You see right away that A3 in this case does not actually communicate to U1 baryon or anything. So this is telling us that BCF in this regard, or the BCF fluxes, talk directly to the domain walls. And again, this is going to play an important role later on when I discuss the axion domain walls. All right, so this basically, ends part 1 of my talk. So let me see whether there are any questions. All right, so let me move to the second part, which is anomalies on non-spin manifolds. So now, generally speaking, putting fermions on some manifold requires a spin structure. And by this, I mean that you should be able to lift the SO4 to a spin 4. If you can do that, we say that M admits a spin structure and M is a spin. But sometimes you cannot do that. If this lifting is obstructed, we say that M is non-spin. A very famous example of a non-spin four-dimensional manifold is the complex projective space CP2, which is defined as the coordinates, the complex coordinates xi1, xi2, xi3 identified with a complex number lambda. In other words, CP2 could be thought of as S5 mod U1. One simple way to see that you cannot put a Weyl fermion on this complex projective space is to compute the Dirac Index in this CP2 background. So the Dirac index, in order to compute the Dirac index, you just, excuse me, you have to compute the contribution from the topological charge of gravity, and you find that it is equal to -1/8. So the fact that the Dirac index is not an integer is telling you that there is something wrong in putting a Weil fermion on CP2. This is why we say that CP2 does not admit fermions. However, there is a way out. The way out is to turn on a U1 flux. So in this case, we define what we call the spin C structure, which is the spin group times U1, and then we mod by Z2 because Z2 is common to U1 and to the spin group. So how we are going to use how we are going to turn the U1 in order to be able to put our fermion on the manifold? I'm going to turn on a flux of U1. So F is the field strength of the U1. And this flux is going to be a half integer flux. So M is an integer plus 1/2 times K. And K is the color 2 form, which is associated to the metric tensor on CP2 like that. And the color 2 form is anti-self-dual. The fact that the color 2 form is anti-self-dual means that F, the field strength of U1, is anti-self-dual, which means that it does not carry an energy momentum tensor, and hence it is topological, and hence it cannot back-react or destroy CP2. So this is very nice. I can turn on a U1 field that does not destroy my CP2. Now I can compute the topological charge of this flux, and I find that this is given by this expression here. And then I compute the Dirac index, which gives contribution both from the gravitational background and from the U1 flux. And now I find that it is an integer, which means that I can use this structure in order to put my fermion on CP2. So now, how I'm going to turn on the BCF fluxes on CP2? I'm going to play the exact same game I played before, just paying attention to an extra factor in order to take care of the fact that CP2 is a non-spin. So again, I have my transition functions, Gij, and these transition functions have to satisfy the co-cycle condition on the triplet overlap of Ui, Uj, Uk. Now, my Gij is made of the following. It is again made of the Gij in representation R of my color group, of the transition function in the flavor group, of the Gij in the U1 baryon. And finally, actually, I'm introducing this Gij of the spin in order to account for the fact that I need some extra flux, U1 flux, in order to put my fermion on CP2. So again, as I mentioned before, that the transition function in representation R in the color group is basically given by the nth root of unity to the power little n. Again, little n is the analyty of my representation. Gij in the flavor group is the center element of the flavor group. And finally, I have to also consider the Gij in the U1 baryon to take the following form. So these two factors are necessary in order to quote unquote absorb these two phases that come from the color and from the flavor. However, I have also to account for the fact that I need a half integer flux in order to put my fermion on CB2. So there is an extra -1 here, again, because my manifold is non-spin. So I can translate that into field strength in the color, flavor, and U1 baryon. So one common feature is that all these fluxes have to be proportional to the Kähler-2 form. This means that all these fluxes don't carry energy momentum tensor and hence don't back react on CP2. Again, the way to turn on the fractional flux in the center and the flavor group is to take f of this form. Again, H are the Cartan generators here in the color direction. News and the news are the weights of the defining representation. The same can be said about the flavor field, and this is the field of the U1 baryon. Again, little n here accounts for the fact that my fermions have a nullity little n, and this extra -1 sign that you saw before translates into this factor 1/2. Again, this is necessary in order to put my fermion on the on CP2. Now I can easily compute the fractional fluxes in the color flavor U1 baryon. And you see here that because my manifold is non-spin, there is an extra factor of 1/2 that appears in my fraction fluxes. And in fact, this extra 1/2 is going to put extra constraints on the IR dynamics, as I will show momentarily. Again, as a consistency check, we can compute the Dirac index of the fermions in this theory on CB2, and we can see right away that it is an integer, which means that these fluxes are consistent on CP2. So now I'm going to play the following game in order to see what the BCF anomaly on non-spin manifold buys us. I will consider a theory, and I will assume this theory form massless composites in the IR. And the way I will do that is that to check that the massless composite match all the zero form anomalies. Sorry. So I have a given theory in the UV, and I will propose massless composite fermions in the IR that match all the zero form anomalies. But then I will turn on the BCF fluxes on the CP2 and see whether the composite fermions can match the new anomalies. So again, ZUV basically is the partition function in the UV in the background of my fluxes. Under a discrete chiral transformation, it picks the following phase. The D, C, DF, DB, and DG, these are group theory coefficients computed in the UV. Now I can take my composites in the IR, and I then compute the phase that my partition function will pick as I perform a discrete chiral transformation. And again, I will find that the transition function picks the following phase. But now instead of D UV, I will have DIR, again in the color, flavor, baryon, and gravity directions. And the matching here demands that these coefficients are exactly the same, but not quite. They actually can match mod 2NFTR. This is important because here I am considering the transformation by a discrete chiral symmetry. So now I can actually play a very nice game. I can try to turn on a flux, one flux at a time. So what I can do is that I turn on the flavor flux without turning on the flux of the color group. And then I turn on the flux of the color without turning on the flux of the flavor. And then I can turn on both the color and the flavor fluxes. This will enable me to find the most general set of Hooft anomalies that I can use to constrain my theory in the IR. This is very strong because now I actually can prove a theorem. So here is the theorem. A set of composite fermions cannot by themselves match the new anomaly, the BCF anomaly on CB2, if the number of flavors is bigger than or equal to 2, and one of these two conditions are satisfied. Either GCD of NC and NF bigger than 1, or GCD of NC and the nullity is bigger than 1. If the number of flavors is bigger than or equal to 2, and one of these two conditions is satisfied, then either composites don't form, or if they form, then they have to be accompanied by partial breaking of discrete chiral symmetry and or TQFT. So this is extremely strong. This is something cannot be said at all about this theories using the zero form anomalies. So in fact, I was not able to build to find an example that satisfies this condition and one of these two conditions. However, here I will present an example for NF equal to 1 Dirac flavor. So I am taking SUN6 with 1 Dirac flavor in the 2-index anti-symmetric representation. This theory enjoys a ZA discrete chiral symmetry. Now let us see how to match the different anomalies in this theory. Here is a proposal. So the first thing you can say that you have to form or you can form massless composite fermions in the IR. And these massless composite fermions match the zero form anomalies, the traditional Hooft anomalies. So if you didn't know about the BCF anomalies, you would stop here. But with the BCF anomalies, you find that actually the composites by themselves are not enough to match the BCF anomaly. You also have to postulate that the 4 fermion condensate has to be non-vanishing, which breaks the discrete chiral symmetry down to Z4. Again, you can show that using the BCF fluxes. But turning on the BCF fluxes on a non-spin manifold tells you something extra. In fact, doing the computation on a non-spin manifold tells you that there is an extra Z2 phase that has to be matched by an IR emergent topological quantum field theory. So this basically is telling you that with turning on these BCF fluxes on non-spin manifold, you have your composite fermions have to be accompanied by extra budget in the IR. All right, this ends my second part. I believe we still have some time, so let me see first if there are any questions before moving to the third part.
If I may, do you have
Yes,
any
please.
example of such gauge theory with quarks in some representation where there is a compelling argument why the gauge invariant bilinear does not condense, but the quadrilinear does condense? Because dynamically, it looks more natural for the bilinear to condense rather than the quadrilinear one.
Not really. So if I understand your question right, you are telling me that why you are forming composites rather than forming condensate. Is this correct?
No, my question is very naive. Let's put aside all these topological constraints and anomaly constraints. There is a question whether psi tilde psi condense or not, and then and if not, whether the quadrilinear that you mentioned, psi tilde psi quantity square condense. Right. So the naive thing is that if anything condenses, it would be the bilinear.
Right.
And of course, the quadrilinear is also non-zero.
That is correct. Yes.
But so my question is there an example where there's a compelling argument that the bilinear does not condense, but the quadrilinear does?
Not really. No. Yeah. I mean, always. Whenever. Sorry. Yeah.
Can I make a remark?
Yes, please.
I think there's a simple example. If you take QCD with one adjoint and NF equal NC fundamental fermion, I believe that in that theory, there is compelling evidence that fermion bilinear does not form in some regime, and some quartic condensate may form.
But is it on R4?
On R4, I'm not 100% sure, but at least on R4, this is like, if you think this theory is a deformation of SQCD by turning on a mass term for the scalar. So at least for a range of mass, this should be the scenario. I am pretty sure of that, even on R4. But okay, I can think about this. Just give me a sec. But then I will comment at the end, probably. Okay.
All right.
Okay.
Okay. So let me, yeah.
Excuse me.
Any questions?
Maybe. Sorry, I actually was slightly off the talk, so maybe I asked something may not be directly related, but let me ask anyway. So the full fermion condensate is actually side, it's like side aside, right?
Yes.
It's not side.
No.
No. Okay.
No.
I think maybe condensed matter people can comment. I think people talk about the Z4 superconductor instead of Z2. In that case, I think maybe Xiaogang knows. Is that type is like side condensate? Is that right?
You just have to form
And
a color
I wonder where the
singlet.
loss phenomena happens. Similar phenomena like side.
No, I think it's really different. So first, let's clarify the notation. I don't think you should call it side dagger, because he multiplies only left-handed fields. So he has no right-handed fields. So that's why he wrote side tilde, where psi and psi tilde are both left-handed fields. That's the way I interpret his notation.
Yes, exactly. That's correct.
And the question is not about the Higgs phenomenon. In Higgs phenomena, you can Higgs the gauge group to various things, but his condensates are all gauge invariant.
Yes.
The gauge group is not Higgs. The gauge group is strongly coupled, and some gauge invariant composite gets an expectation value. And the question is about that. So the examples that Juven just mentioned, where the U1 is Higgs down to Z2 or to Z4, that's a totally separate question.
I see. Yeah, thank you.
Okay, thank you.
Nati, do you want an example on R4, or is R3 times S1 fine?
You know, I'm in no position to bug you. If you can offer any interesting example, I'll be interested.
So if you take, for example, two-flavor Qcdr joint on R3 times S1 and impose periodic boundary condition on the fermions on S1 and go to the small circle regime, only the discrete chiral symmetry breaks in the small circle. Only the determinant condensates acquires a wave. So it's a 4 Fermi operator. And the fermion bilinear does not. So continuous chiral symmetry does not break, but discrete chiral symmetry breaks. So at least on R3 cross S1, there is such a possibility.
I see. I thought that Dumitrescu, Cordova, and maybe Trilligator was also on that paper, had such examples by deforming the 4-dimensional n equals 2 theory. But you guys should remember better than I do.
Yeah, I am pretty sure on R3 cross S1, this is the case for Qcdr joints on small circle.
Yes, on R3 cross S1, always the continuous chiral symmetry doesn't break.
Yeah, in
yes.
naive construction. So
that is correct, yes.
But discrete part breaks, and it is, for example, in the theory, I said it's 4 Fermi operator.
Yes. But if actually, if I recall well, okay, Cordova, Dumitrescu, when they consider n equal to 2 and this connection to Qcdr joint, they proposed some scenarios, right, where the 2 fermion condensate doesn't form and the 4 fermion condensate does form. But this is a scenario, but one possible scenario. It does not say that the two fermion condensate does not form. All right. So maybe I should move ahead, okay, to the third part. So in the third part, I'm going to discuss.
Let me ask one more.
Yes, sure, please go ahead.
So you have a 4 fermion condensate, let's say.
Right.
Do you know any phenomena even go to like 6 fermions? In a similar theory that you study?
In principle, as long as, well, I don't have something in my mind right now, but in principle, okay, I mean, if the 6 fermion, I believe there is example but I don't have it in my mind right now. But I believe that if you just if your 6 fermion condensate match the anomaly, then it is possible. But again, it does not tell you that the theory will that the 2 fermion on the 4 fermion condensates are excluded as possible scenarios.
Juvan, on R3 cross S1, if you take 3 flavor Qcdr joint, that's what you get. You get a 6 Fermi condensate, just in the line that was just discussed.
Okay.
About R4, I don't know. But...
All right. Well, the reason I ask is from the QCD finite density phase with chemical potential, you know, the color flavor locking superconductors. There's a phase that the color flavor lock, the 6 quarks can have a condensate. I asked this just for that reason. I don't know. I think the theory is different, but I mentioned the 6 quarks because that reason. Yeah. Anyway. Well, thanks, Eric.
Mm-hmm. All right. Axions. So I mean, in this third part, let us do something extra. Let us couple the vector-like theory I told you about before to axions, sorry, a complex scalar field phi. So phi here is a complex scalar field. And this is Mexican half potential. Actually, there is a missing square here. And V is the VEV. And I will also introduce a Yukawa coupling between my fermions and the complex scalar phi. And I will demand that my VEV of the complex scalar is much bigger than lambda QCD. Of course, the Yukawa coupling will break the SUNF1 cross SUNF2 down to SUNF vector. Now, my complex scalar can be written down as the magnitude and the phase e to the IA, where A is my axion. And my theory also enjoys a discrete chiral symmetry that acts on the complex scalar and the fermions as follows. Now let us try to construct the effective field theory of this model at different energy scales. So first of all, let me flow to energy scale that is much smaller than the VEV of my scalar, but still much bigger than lambda QCD. In this case, I can put the magnitude of phi equal to the VEV, and this means that the fermions get very massive and they decouple. So basically, we have an emergent one-form center symmetry in this theory. As you go to energy scales, much smaller than the VEV, but yet much bigger than lambda QCD. Now you can write down the following effective Lagrangian in this energy scale. This is the kinetic term of the axion. And this is how the axion couples to the topological charge of the color field. And this is the kinetic term of the color field plus dot, 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 which represent higher order corrections. Yet you can also flow to energy scales much smaller than lambda QCD. And now you can use instanton calculus in order to compute the potential of your axion. So basically, you can try to write down the following effective field theory in the IR. This is again the kinetic term of the axion. And this is the potential that results from summing over instanton and anti-instanton pairs in the partition function. This potential, however, is not under complete control because we are dealing with strong dynamics. However, it captures the essential symmetries of your theory in the IR, and in particular that the theory admits NFTR vacua. So basically, there will be domain walls interpolating between the different vacua of your theory. And these domain walls are going to be extremely wide because the width will be basically the inverse mass of the axion. And the width is basically given by V over lambda square, which is much, much bigger than 1 over lambda QCD. One also can write the following trivial TQFT that accounts for the fact that you have NFTR vacua. And this exactly looks like the TQFT that we wrote before when we were constructing the Wisdomino-Witten action. Again, here A is the axion and A3 is the three-form field that couples to the three-worded volume of the axion domain wall. So you see here, as you actually make a large field excursion, you go from one vacuum to the other, but there is some problem here. It seems that this effective field theory doesn't see the BCF anomaly. So the question is how the BCF anomaly is being matched in this theory. So here I propose that the matching will happen by enlarging the TQFT, the trivial TQFT I just wrote down, in order to include the BCF fluxes. Here I am again considering NF equal to 1 for simplicity. So you see that this action now takes the exact same form of the Wisdomino-Witten model. And the axiom basically plays the role of the theta, plays the role of a dynamical theta angle, if you want to think of it like that. Now, as I mentioned before, that the free-form field it talks to the center of the group, which is telling us that there has to be some non-trivial dynamics happening on the domain wall in order to match the BCF anomaly. So I propose, or we propose, that there is a Chern-Simon theory that lives on the domain wall, which is necessary in order to match the BCF anomaly in the bulk. So this is not a proof. However, this is a consistent story, at least at this level. And one I can argue for the Chern-Simon theory by thinking of a four-dimensional manifold as having a boundary, and the boundary is our domain wall. Now we can integrate by parts to find that there is a Chern-Simon theory that lives on the domain wall. So in order to match the anomaly, we propose that there has to be, again, a Chern-Simon theory that lives at the core of the domain wall. And this is necessary in order to match the BCF anomaly. So this Chern-Simon theory is telling us that there has to be some non-trivial intertwining between the heavy degrees of freedom, which is the QCD degrees of freedom, and the light degrees of freedom, or the axion, as the axion makes a large excursion between two vacua. Notice here that this intertwining between extremely different scales, because the scale of lambda QCD is basically lambda, and the width of lambda QCD, the width of QCD is lambda to the -1, and the width of the domain wall is V times lambda to the -2, which is extremely large compared to lambda to the -1. So I just told you that the theory enjoys an emergent one-form center in the bulk, but now because there is a Chern-Simon theory that lives in the domain wall, and we know that the Chern-Simon theory is a gap theory, then we expect that the quarks will be deconfined on the axion domain wall. So basically, we are saying that this deconfinement of the axion domain wall is a result of matching the anomaly, the BCF anomaly between the bulk and the domain walls. Well, this is a strongly coupled theory, so I cannot prove it. It is a consistent picture. However, one can see the exact same phenomenon analytically if we formulate our theory on R3 cross S1. If we formulate our theory on a small circle. So basically, we can take a small circle, okay, such that its circumference is not.
I have a question about the
Yeah.
previous picture.
Sure.
So the fact that you have an axion doesn't really play any role here. The only thing that matters is that theta varies in space.
That is correct. Yes.
So you can, instead of adding the axion and its kinetic term and the scale mu and all that, you can just say that theta varies in space between 0 and 2 pi.
That is correct. I agree. Yes, that is correct. Yes.
Then there are very strong arguments telling you that this must happen.
I see.
Even without saying anything about anomalies. For example, in many of these theories, you have confinement on one side and oblique confinement on the other side. So these are different monopoles condensing on the different sides. And therefore, on the domain wall, neither monopole condenses. And therefore, we have deconfinement.
I see. I see. So you are telling me that this is a general phenomenon which will always happen whenever there is some theta that varies between 0 and 2 pi in this case.
Yeah. Whenever the physics, the object that condenses at 0 and 2 pi is, whenever this object is not the same, which is almost always the case, then there's a different fields condensing on the two sides, and therefore no field condenses on the interface between them.
I see.
The main thing is that the axion doesn't play any role in your discussion. Like, we can think of it as a classical background field.
Thanks for the comment. So, but this is strongly coupled phenomenon. Let us try to see it actually in a weakly coupled regime. So basically, if you put your theory on a small circle, then you can actually see the exact same thing happening, but you can compute it analytically. And this class of models, okay, of putting the theory on a small circle was started more than a decade by Midhat Ansal and Larry Yaffe, and it has been very popular. And actually, we have understood we understood a lot of phenomena on the small circle that are otherwise extremely hard to understand on R4. This is a very long story, and in order to cut a very long story short, let me just give you the upshot here. So I started with my 4D theory and then compactifying on a small circle again, such that the inverse length is much bigger than lambda QCD. And in this case, I can dimensionally reduce from 4 dimension to 3 dimension. And in 3 dimension, the theory will abelianize. It will be fully abelian field theory. And in this case, I can talk about photons, which are in 3D. They are compact scalars, and these photons are going to play the role of the strong dynamics in R4. Again, this is a very long story, but here I am just writing down the effective field theory of this of QCD on R3 cross S1 coupled to an axion. And this is not, again, this is not a model. You can actually do a reliable semi-classical computation in order to get this effective potential. Again, A here is my axion, and sigma is the photon. And is a complex scalar. And this theory confines in the IR, as you can see here, that the theory has a mass gap. The photon is massive. This is basically the Polyakov model lifted from R3 to R3 cross S1. The nice thing here that the theory enjoys all the symmetries that theory in R4 has. Here I am also keeping the exact same hierarchy of the scales that are used on R4. So first of all, I am taking the VEV of my complex scalar field to be much bigger than the inverse length of my circle. And also, I am demanding that the mass of my axion to be much smaller than the mass of the photon. The photon is a complex scalar, again, and this enables me to compute the electric field due to this photon. And this will actually be important in what I'm going to say next. So now this is a potential, and I can plot this potential in the sigma A plane. So I get the following density plot. Basically, here I'm taking NFTR equal to 3 just for illustration. I have 6 vacua, and these vacua are represented by the blue circles here. And let us try to understand what happens between these different vacua. So one can solve this model analytically to find that there is a domain wall that is interpolating between one vacuum and the other, as you can see. There is also another domain wall that is interpolating between this second vacuum and this one is identified with the one that is here. And one more thing is that because of the symmetry of my potential, the tension of this, first of all, this is a domain wall that is interpolating between these two vacua, and the tension of this domain wall is exactly equal to the tension of this domain wall because of the symmetric structure of my potential. We can also compute the profile of the axion in the domain wall, and we find that it is associated with a non-trivial profile of the photon, as you can see in this picture here. So again, I told you that this theory confines. So just believe me that a fundamental quark in this theory has a flux of 2 pi. Now, because the axion domain wall carries a photon inside, we can compute the flux that is carried by this domain wall. There are 2 main domain walls, as I mentioned, one interpolating between 0 and pi, and the other is between pi and 0. So this domain wall carries a flux pi, as can be computed from here. And because a single fundamental quark carries a flux equal to 2 pi, this means that the quark anti-quark pair will be confined due to the formation of 2 domain walls like that, such that every domain wall carries half the flux. Now the rest is simple, because basically what you can do is that you can take one of the domain walls, for example, this one, and you cut it into half, and just mentally take these 2 halves to plus and minus infinity. And so you get this picture. The important thing to notice here that all these domain walls have the exact same tension. And because of that, it doesn't cost me any energy to move these quarks apart. This is exactly the deconfinement of the quarks on the domain wall I have just told you about. So this is basically the analytic way of seeing the deconfinement on the domain wall on R3 cross S1. So let me now just to come to a conclusion and overlook. So Hooft anomalies give us a unique non-perturbative tool. And as I mentioned, that the more anomalies we have, the more restrictions on our theory. They provide a new venue to understand all the new phenomena. For example, the deconfinement on axion domain wall. Actually, they can also be used to understand the phenomenology of axion inflation. Examining the BCF anomalies for other groups is also important. For example, one might want to test some of the confinement in the SUSY theory when we turn on these BCF fluxes there. Also, we haven't exhausted all the backgrounds. So, for example, the question is whether we can turn on BCF fluxes and combine them with turn them on non-orientable manifold. This enables us to find more anomalies, maybe. And also that we can use these generalized anomalies to study the physics of chiral gauge theories. One also would like to combine the anomalies and the QCD on a circle for a better understanding of the strong dynamics. And finally, one have to see in the future more direct connections between these theoretical constructions and phenomenological studies. Thanks a lot.
Thank you very much, Mohamed, for a very nice talk. So we have some time for questions. If anyone has a question, feel free to unmute yourself. Well, we had some discussion already during the talk, so I think what I'll do is I'll stop the recording, and then if anyone wants to stick around and discuss, they can feel free to. Okay.
Nice talk. Thank you.